forward to the cloud. All right, so we're talking about arc length polar graph, and you know, we can get into the bits and pieces of this in terms of a derivation, but we kind of already sort of beat that to death a little bit when it came to the arc length formula for parametrics. And so you look at this and you compare it to that, and you see that it has a lot of the same characteristics, right? It's the square root of, in this case, r squared plus drd theta squared, right? So as opposed to having functions of x and function x in terms of t, y in terms of t. So function of x, function of t, what I meant to say. So yeah, we could spend time deriving this, but I think I know my audience well enough to know that maybe we don't want to do that right now. All right, so we're going to jump into an example. Just for the ability to point at something, I'm going to copy this over and bring it with me. You know what, just to be safe, let me save it also. So let's just grab number 4 on the top of page 15, just so I could show you what it's like to tackle this using arc length, because we already know what this is going to boil down to in terms of, because if you look at the work that we did on page, I'm kind of flipping around here, but page 14, all that area stuff, you kind of know how it's going to play out area-wise, but how is it going to play out in terms of arc length? So let's investigate. All right. The good news is it's a plug-in ready formula, plug and play. All right. So I needed the RD theta. That part is easy enough. All right. So pop in the old drd theta by first finding drd theta. In this case, 3 cosine theta. We need an interval. If we're going to find the arc length, we need an interval to work with. So for that, you know, you may want to get Desmos involved. You may want to do a quick sketch. You know, bottom line is you need to know where this this curve exists. So, and when you do figure out where it exists, you want to determine how long it takes to complete a cycle. Right? So let me bring Desmos on board here. Not Calendly, I don't know where that came from, Desmos. We need a graphing calculator. We need it to be set up for, oops, I hit the wrong thing. We need it to be set up for polar graphs, right? So I hit that little monkey wrench, I accidentally hit the settings key, but it just kind of goes to show that it's easy enough to stumble your way to the right settings. So then I select the polar one. Right? So then we got that all set up. I'm going to type in r equals the sign. So I'm going to go to functions of theta. So again, in the interest of avoiding hunting around looking for a symbol, I just start typing in the one that I want. Right? Now it defaulted to 0 to pi as an interval. So I can go with that and take a look at what I have graphically. Now that's the beauty of technology. You have the ability to just kind of rely on it to sometimes know what the domain ought to be, you know, especially with Desmos GeoGebra. So here it's saying, I mean, my instincts would say go to 360, 2 pi, but here Desmos is saying, no, just go to pi, right? So let's just take a look and see what would have happened had I gone to 2 pi. Same circle, it just went around twice, right? If I went 3 pi, same circle just went around 3 times. But if I go pi over 2, same circle just went around half, right? So using properties of symmetry, you get the idea that, all right, well, if you're only getting halfway through the circle from 0 to pi over 2, then it would make sense that you're going to go all the way through the circle from 0 to pi, right? So Desmos kind of got you there, but sometimes we don't want to trust the technology. We want it to be kind of firm in our heads that this is how it's going to be. And what I like to do, and it seems like maybe a little bit of overkill, what I like to do is I take the given setting and I just dial it back by a smidge. So like pi minus point, let's say 0.1. Nah, maybe that's too much of a smidge. It's got to be something recognized. I'll say 0.05. Oh, I lost my pi. I got an extra decimal. I keep hitting it. I don't know why. Right? It's hard to see in this view, but if I bring it in, you could see that it comes just shy of hitting one complete cycle. All right, so that for me is kind of like proof positive that, all right, it's pi, because if I go just a little bit short of pi, I get a little bit short of having a full circle. All right, that's my way of thinking. My way of thinking kind of gets me there, but you may not need to do that, and that's perfectly fine too. All right, so it's just a strategy, just a thought. Some people hate that strategy, and other people are like, that's a great strategy, I love it. So, you know, figure out where you fall in that. So 3 cosine theta. Oh, sorry, 3 sine, I was reading the wrong thing. 3 sine theta. I mean, it's not going to matter because it's commutative, but in order to model it by the formula, I want to have it in the right order. Plus 3 cosine theta, that quantity squared, d theta. Now, this one's going to be easy enough to take through by hand. You could figure out the result to definite integrals using technology, but we want to also be proficient with doing some of this stuff by hand, because later on when we have to change the parameter in parametric equations, it's going to rely on you being able to solve an integral by hand. So, you know, will you always have to do it? Of course not. When will you have to do it? When it asks you to, specifically on a test. If it says, put it, you know, show all work, show all steps. And I take that extra step of saying you may not use a technology for this problem. You know, you gotta show me all the steps. But I don't do that for more than one problem, maybe 2 problems on a test, right? So depending on the subject. So I can clean this up a little bit. I'm looking at the radical's still there, but if I square each quantity, I'm looking at 9 sine squared theta plus 9 cosine squared theta, the whole thing d theta. I have a common 9 that can be factored out. So I can take it out of the whole thing, right out of the integral. But you could also leave it in the integral as a constant multiple if you want to. It doesn't make a difference. That's something you should remember from Calc 1 and 2, Calcs 1 and 2.
Would it be 3 or 9?
It would be 3, thank you. So sine squared theta plus cosine squared theta, d theta. Now, as long as you know your Pythagorean identities, you're in good shape here, right? So now it is an identity, so there's ways to verify it. You can verify it with technology, you know, just typing it in and seeing what you end up with as a result. And it should end up being 1 because it doesn't matter what the value of theta is, right? But yeah, it's just life is a little bit easier if you know that fact, right? So this is 1, square root of 1 is 1 d theta. Then we're going to be integrating, so 3, and that's going to be times the integral of 1 is theta over the interval of 0 to pi. Sub in, we're going to get 3 times pi minus 0, which is just the same as saying 3 pi. And now, if you think back to what an arc length really is, it's a length around a curve, you know, from beginning to end, you know, designated starting and end points. So I can check this because that should be equal to the circumference. C equals 2 pi r. Okay, well, looking at this figure here, it seems that we're looking at a radius, right? So we have a radius of 0.5. Well, actually, it should be 1.5, so I don't know. Did I type it in right? No. Sorry. Radius of 1.5. Pop that in. 2 pi times 1.5 is equal to 3 pi. Yeah, 3 pi. All right, and that's what it ought to be. All right, so just check it with simple geometry. All right, it does, of course, rely on me having typed in the original equation correctly in order to pull out that radius, but, you know. But that's sorry?
R is supposed to be 1.5.
Say it one more time.
How do you know that R is supposed to be 1.5 and not 3 pi?
How do I know? I'm just looking at the circle.
Oh, okay.
Yeah, diameter is 3, so half of that's got to be R of 1.5. So, and actually, as it turns out, you get an idea that looking at this function, R in terms of theta, you get the idea that, all right, well, functions that take on this form are going to be circles where that leading coefficient is the diameter, right? So this is a circle. Let me just bring it in. Diameter equal to 3. All right. Now, you may also wonder, okay, so what would it be like if it were a cosine function? And, you know, the short way of saying that would be, okay, well, let's just take a look. But it has to do with symmetry, right? What it's symmetric about. Right? Oh, I have to, I mean, I guess that could work, but that's not what I intended to do. Cosine theta. All right, so if a question said 3 cosine theta, you see it's got the same characteristics. Diameter is still 3, you know, just eyeballing that. Right? It's still a circle, it's just symmetric about the x-axis instead of being symmetric about the y-axis. Right? So, you know, it's got little twists and turns here, but there are some things that you can kind of hang your hat on. So this is the arc length. All right. So looking at, well, number 4 actually makes more sense if it's an area question. Number 6 is pretty much the same as what we just did, so it'd be kind of overkill to do that one again. Actually, 5 and 7 are both kind of area questions, so I'm going to just move on to the next page and find one that that kind of fits the arc length concept. All right, I'm gonna modify number 7 on page 17. So not the area of the overlap, and maybe, you know, we could also tackle the area question, although it's on, you know, an answer key online too. So find the arc length created by the overlap between R equals 4 and R equals 8 cosine theta. And all of these are fair game for typo bonus. Anytime I make a change to the packet, even if it's a short-term change just for you all, and I have no intention of modifying my notes for a future semester, I'll still take it as typo bonus. I just want to make sure everybody has an opportunity to get some bonus credit for typos. So the more opportunities, the better, in my opinion. So R equals 4, that's a simple one, that's a circle, radius 4. Then we have R equals 8 cosine theta, which we just learned is going to be along the polar axis. And it automatically computes the domain for us again, so that's wonderful. There's just one less thing to worry about, because people have that kind of issue pretty much all the time, where it's like, I can type stuff into a calculator, I can solve equations. The only thing I ever really have trouble with is the domain. And so if that's the case, then this may make things a little bit easier. In terms of the sketch, now I know what it looks like. I'm just going to go by twos. So instead of 4 rings out, I'm going to go 2 rings out and draw a circle. And then instead of going 8 out, I'm going to go 4 out from the pole. This one's a little trickier. Okay, in terms of drawing it, because you don't really know how far up and down you're supposed to go. And I don't want to tell people that they'll have to go get compasses, in order to draw a perfect circle. So it's just eyeball it. You know it's going to have the same radius as the other circle, the r equals 4. So you got a sense of height. Mine went a little bit high, but that's okay. Okay. So what we're looking at here, and I'll just kind of emphasize it just by sketching over it, is I'm looking for this guy and this guy. Now, that's the best possible news, because we have symmetry here. All right. If I figure out one, I got the other. That's great. But it does seem as though I need to know where they intersect in order to know how to bound my integral function. Okay. So I'm going to set them equal. And that old chestnut, the classic calculus technique, or I would even go back and say algebra. If you're in doubt, you only have a few possible avenues. Set equations equal to each other, set them equal to 0. When you throw in the calculus, you take the derivative, set it equal to 0, but there's only so many different avenues that you're going to use when it comes to solving problems. So, when in doubt, just choose one of those things. All right. So we're looking for the intersection between r equals 4 and r equals 8 cosine theta. All right. And again, we want to be prepared to do it by hand, so I'm not going to go into how to do it on Desmos right now. There is way when you want to solve equations, it's pretty straightforward. But for now, we'll just focus on the by hand approach. So 4 equals 8 cosine theta. Divide out the 8, we're looking at cosine of theta is going to be equal to 1/2. And if you know your unit circle stuff, we know that that's talking about pi over 3. It wouldn't be 2 pi over 3, because 2 pi over 3 is, for cosine, is negative because it's the second quadrant. Same idea with 4 pi over 3. So then we'd be looking at 5 pi over 3. Now, and so on. We do have domain considerations here, though. Right? So we do have to worry, well, I wouldn't say worry, but we do have to be mindful of the fact that one of the circles exists on the interval of 0 to 2 pi. The other exists only from 0 to pi. All right? So we might end up overdoing it if we're not careful. So for that, I go back to my Desmos and just take a look, because really, as long as I can come up with the, and by the way, it kind of looks like it is pi over 3 and 5 pi over 3 just by looking at the picture. That can be kind of unreliable in some cases, but here I would kind of, I wouldn't say I bet my life on it, but I'm very, very confident that pi over 3 and 5 pi over 3 are correct, because I mean it's going right through those angles. Right? So what I'll do is I'll just dial down my r equals 8 cosine theta function so that it only exists from 0, for example, 0 to pi over 3, and then see what that looks like. But in the end, if you have a choice, because we're talking about symmetry between the two equations, so you only get that piece. And so then I would say, okay, well, maybe it's pi over 3 to 5 pi over 3. But if you have a choice between the two functions, I would hope that you wouldn't be looking to use the more complicated function. So it's pi over 3 to 5 pi over 3. That gives you the whole thing again, because what it's doing is it's starting at pi over 3. And actually, that's weird. I don't think it should be doing that, but it is. It should only be going to 5 pi over 3. But oh, yeah, because it's got to go the whole rest of the way. Yeah, so since the circle only exists between 0 and pi, when we're going from pi over 3, we're telling it to go pi over 3 to 5 pi over 3. We're saying complete the loop and then go an extra pi over 3. So that's Desmos is getting confused by what we're asking. So if I were to just leave this as pi, I get kind of sort of what I'm looking for, but it's starting to get a little crazy. So instead, what I would say is let's take a look at the circle and see if we could trim that down, because the circle is going to be easier to manage. And what you see is what you get. If I want to go from, for example, 0 to pi over 2 in a circle, that's only going to give me the part of the circle that exists in the first quadrant, right? If I want to go from 7 pi over 2 to 11 pi over 2, that's going to it'll get confusing visually. But that's only going to give me that interval. It's just because it will have gone around multiple times. It'll appear as though it's giving you more than what you want, and that's the drawback of using the 8 cosine theta, right? But if I look at r equals 4, so I'll just jot this down here. So plot r equals 4 from, and it's a question of where to where. So I can go from 0 to pi over 3. I can go 5 pi over 3 to pi over 3. Now, I got to be careful with that. I'll highlight this. Logically, that would be an issue, because you can't go, if you're creating an interval, you're not going to go from a larger value to a smaller value. So what we'd have to do is find the negative coterminal for this and call this instead, I would say negative pi over 3 to pi over 3. So those are some possibilities. Now, if I go from 0 to pi over 3, I would just have to remember to double that result, actually quadruple it, right? Because 0 to pi over 3, just going back to the diagram, let me really emphasize it. 0 to pi over 3 would just be this piece, right? And since I have 4 symmetrical components, I would just need to know that I got to quadruple that. Double it to give me the part on the r equals 4, but then double it again in order to give me the part that's on the r equals 8 cosine beta. So a lot of different possibilities, and there's even more possibilities, but those are the 2 most popular ones, I would imagine. So what I'll do is I'll just do the 0 to pi over 3, right? So 4 quality 4, going from 0 to pi over 3. We're going to have our radical. All right, it's r squared plus dr d theta squared. All right, well, we know that r is equal to 4, dr d theta, constant value is going to be equal to 0. All right, so 4 squared plus 0 squared, much easier in the integration front also. All right, so we're looking at just a clean 4 inside. So 4 on the interval of 0 to pi over 3, 4 d theta. You can consolidate if you want. We'd be looking at already the 16, 0 to pi over 3. And then that would be a 1 d theta. So 16 theta on the interval of 0 to pi over 3. 16 pi over 3 minus 0, which in turn just gives you 16 pi over 3. All right. Now, this question, so this would be in terms of units. This question didn't give us any context. So I don't know what the units ought to be. That actually seems reasonable size. I don't know what the units ought to be, like feet, inches, miles, whatever. So I just leave it as units. On a test, you could just leave it as a numerical value, but just be mindful if there is context, then you'd have to include the units. Otherwise, you would forfeit some credit. Right? We don't want to be in a position for that kind of thing because of the obvious reasons. You know, like you're losing credit on a test for a mistake that has nothing to do with the calculus of it, right? So, and I know plenty of students over the years, many students who, you know, they never got an A in a math class, but they're really good at math. They understand the concepts. They just always made those careless mistakes. So just be mindful of that kind of thing. I'm not very nitpicky about a lot of stuff. That's one of the things that I am pretty particular about. All right. So I'm going to hop back and just do an area question before moving on to the derivative and then vectors. All right. So flipping back, let's take a look at. I mean, these are two similar problems on page 16. So we can just tackle number 5 and see how that goes. And then you know, my theory or my thinking when it comes to this kind of stuff is, you know, if you're having difficulty with it, then sucks to be you. No, it's more like, let me go over an example and then give you another opportunity to try the examples again, and then take questions, you know, at a later time, because I think that logically makes the most sense. If I do both of these examples, then it's like, well, you didn't give me a chance to do any thinking. Now I understand that you know how to do it. You just don't understand how to do it yourself, you know. So that can be frustrating. So can, you know, me explaining my thought process on like everything, that can be frustrating also, I know. But I tend to do it because I need to buy myself time as I'm typing stuff in. As simple as that. All right, so there's my graphs. And you can see, again, it auto-populated the domain. And I gotta say, full disclosure, I either didn't know or I forgot that Desmos did that for us. So that is such a pleasant surprise that that I'm pleasantly surprised. I don't know where I was going with that, but it's great, because one of the biggest challenges with the TI-84 was always like, all right, zoom fit, zoom standard. What do I put in for the domain? Well, try something. If it doesn't work, try something else. Here, it's doing it for you. I mean, that's pretty nice. And we have an agreement with our domains for the two functions, so that's even better, right? So we're not going to have to worry about any kind of funny business. Okay. So I just want to get this on paper real quick. So a radius of 4, and by radius I mean diameter. All right, kinda. And also radius 4. I don't need to scale anything here. And I keep saying radius. I have no idea why I keep saying that. Right. It looks like the intersection's happening smack dab on the 45. So I'm going to try to make it look as close to that as possible. And by doing that, I completely failed. I was looking at the wrong marking. And so I'm just going to move, maybe resize a little bit, because I want it to be somewhat reminiscent of what's actually happening here. all right. I mean, it's not terrible. I mean, I'm just saying that to be a wise guy. It looks gorgeous. I mean, it's beautiful. It's and you see what my hand drawn images look like before it's auto corrected to this. So you can tell that if anybody's benefiting from this, it's certainly me. Right. So the conjecture here is that we're looking at an intersection at theta is equal to pi over 4. Not because of the way I drew it, but because of the way it appeared on Desmos, right? And how did I know pi over 4? Just to preempt the question that might come through, I'm looking at the pi over 6 and the pi over 3 and the stray line in between the two, and I'm thinking back to everything I know about the unit circle. And, you know, in the unit circle, what's between pi over 6 and pi over 3? Pi over 4, all right? So that's where that's coming from. So let me pause a sec. All right, so yeah, and I'm very comfortable and happy and thrilled with this this development in Desmos, but there's still part of me of like, you know, I'm a student, my grades riding on this. I mean, am I really going to take the chance that just because it looks like it's pi over 4 that it really is? And if your answer to that is yes, yes I am, perfectly fine, but I'm a little bit more particular when it comes to this sort of stuff. Personally, I look at it as like I can't let my A be hanging in the balance just because I'm just going to eyeball it. So now that being said, if I go to try this step and I don't know how to do it, then I have no choice. All right. But here I'm looking at it and I see sine of theta is equal to cosine of theta, just dividing both sides by 4. That's a good development. You kind of stray from the algebra and kind of go towards the conceptual understanding of the unit circle, because this is really, I mean, it's a statement, but it's really a statement that's asking a question. Where on the unit circle is sine of theta equal to cosine theta? Now, also, we got to keep in mind that we're focusing on the interval 0 to pi, right? So you could even throw in there on the top half you know, because then it becomes a matter of saying, all right, I can disregard a lot of stuff just by focusing on the top half, and then throw in addition to that, x and y value are equal, right? And what I mean by that is for the coordinate, right? So thinking about the unit circle, you think about, we got a pi, geez, radical 3 over 2 comma 1/2. We got a radical 2 over 2 comma radical 2 over 2. We got a 1/2 comma radical 3 over 2. Then we start getting into the second quadrant. It's just basically asking under what circumstances, for what angle would the two coordinate values be the same as one another, and that happens when theta is equal to pi over 4. All right, so we have that. That's great. Doesn't always play out that way. Sometimes you got to do the work, but when you don't have to, it's kind of nice. Now, I need to figure out the area. So the area outside of 4 sine theta, so outside the red circle, and inside 4 cosine theta in the first quadrant. All right, so it just got like a little bit crazy here, because what it's saying is I want to be outside of the red circle, right? So everything but the red circle, but I got to be inside the black circle, right? But I also got to be in the first quadrant. All right, so it's asking me for, and I'll shade it in green, not that green, something brighter. It's asking me for this area. All right. So what I get from this is I need to figure out the area of that little almond. You know, I don't know what else to call it. Stewie's head. I don't know. I'll do it in this light colored blue. I need to figure out what this is, and then subtract it from the semicircle. All right. I'm going to get it out of there because I don't want people to think that that's actually what I'm looking for. Right. But along the way, we'll have to figure out that value. Right. So that's a benefit of figuring out the theta equals pi over 4. Right. So as far as the semicircle is concerned, we'll figure out the circle area and then just chop it in half. So that part we're not concerned with. It's that almond thingy that we're looking for. Right. So what I'm going to do, and this is kind of like a, I don't know how to describe it except to say that I'm kind of convinced that one of the main reasons I know this strategy, not because, you know, like I created the problem and all that stuff, but because I taught pre-calculus for years, like years. And this concept, the area of a sector, an area of a segment, came up so frequently that when I see it, it just kind of jumps off the page at me. So what I'm doing is I'm kind of, I'm really bisecting it. I'm just kind of cutting it right in half. And I'm saying to myself, all right, well, I got, for my red circle, for example, I got a circular segment that extends from the first intersection point between the two circles to the other, right? So we're going to have a theta value, and I think that theta value is pretty easy to identify visually, but we'll also figure it out anyway. That appears to be a right angle, right? So what I'm going to do is I'm going to go back into my basket of pre-calculus knowledge and steal a formula known as the area of a segment formula. And I'll write it as a circular segment. All right. And that formula, area is equal to 1/2 r squared theta minus the sine of theta. This formula has a whole derivation, and it's wonderful. It has to do with, I use the law of cosines to derive this formula, but that's different story for a different life, I guess. But also, I wanted to point out that at some point in this problem, the calculus needs to happen. It doesn't have to happen for every little fine detail. That's a me policy, right? So if I give you a question like, find the area contained within the function r equals 4, the polar function r equals 4, on a test, you'd have to do it using the calculus way, because if you were to just pop that into area equals pi r squared, you would have solved an entire problem without using a calculus step. In order to give you credit, I need a calculus step, right? You can't solve a problem completely without including a calculus step and expect to get credit for it, right, in a calculus course, right? But my stance on this is, as long as the calculus happens in a meaningful way at some point in the problem, I don't really care where you use the calculus, right? So what I'm going to do is I'm going to use probably the easiest part of this problem as my calculus step, just to trim down the amount of integration that I have to do, or at least the level of difficulty of the integration, right? So, I mean, because here I can easily come up with that area, and I'll emphasize it again. It's, assuming I remember to turn my pen on. This is what I'm going to get from this formula. And I know if I highlight everything, it's like I'm highlighting nothing, but hopefully it makes sense. This piece here is the area of the segment, all right? And so by doubling that, I'll have that little almond-shaped thing, all right? And then I just got to use calculus somewhere else. I'm not going to use the calculus for the hardest part of the problem. I'll use it for the easiest part, right? That's strategizing. The cliche, the work smarter, not harder cliche. All right. The radius of that portion of it is 2. The radius from the center of that segment's circle is 2 units. So I'll just jot a 2 there. The theta is pi over 2. It's got to be in radian form. Minus sine. Oh, sorry. Is it pi over 2?
Pi over 4?
No,
Or
it
pi over
is
2?
pi over 2. The angle is pi over 2. It's just like I mentioned earlier that I would justify that with you all, and I never did. So it's like, is it pi over 2? I think I'm just going to go with it for now. And then I'll come back to explaining how mathematically we would have justified that that's actually pi over 2. I think that's what I'll do. But it is definitely pi over 2 because we're not looking for the angular placement on the polar graph. We're going right back to central angle from geometry. You know, is that a right angle? Yeah, it's a right angle, so that would be pi over 2. Right? But yeah, if we wanted to plot from the beginning of that segment to the end, then it would be pi over 4 because it's only 1/4 of the circle. Right? So that part it's a little weird and it takes a lot of getting used to, but that's, I think, where the power of the Desmos calculator comes into play big time. All right, so we're looking at 2 here. Pi over 2 minus sine of pi over 2 is 1. So we have, and I'll clean it up, pi minus 2. Right, so that's the area of that circular little nugget there. Right, now we want to double it in order to get that almond piece. All right, so we're going to double it. And you know what, instead of referring to it as an almond and confusing everybody, or anybody who doesn't appreciate almonds the way I do, the area of this guy. We're looking at 2 pi minus 4. All right, so that's that piece. All right, so then I just need to find the area of the semicircle. And then once I do that, I subtract this off and I have it. All right, so the area of the semicircle. And like I said before, I want to use the calculus on the easiest part of this. So area of the semicircle. Can handle it one of 2 ways. One way would be to find or use the domain for the entire circle, find the area of the entire circle and then chop it in half. The other way to handle it would be to determine what the domain would be for just that top half of the circle. There's no way that's righter or wronger than the other. And so what I'm going to do is I'm just going to use the area is equal to 1/2. We know that the domain goes from 0 to pi for the whole circle, but if I chop that area in half, I'm going to be good to go. All right, we're looking at 1/2 r squared d theta. So 1/2 r squared d theta. Now that circle, I think I actually need a little bit more width. That's the black one, which I plotted representing 4 cosine theta. So I'm just going to jot 4 cosine theta. All right, so again, we'll theta 1/2 r squared d theta. All right. So whatever this is going to amount to, it's definitely going to be a lot easier than the circular segment formula in like that whole thing in an integral. So that's my thinking there. So we'll clean it up. Area. I'm going to go back to black. So 1/4 interval 0 to pi 16 cosine. So I consolidated I did it in my I explained it to myself. I didn't explain it to anybody else. I consolidated the 1/2 and 1/2 to make the 1/4. All right. So 16 cosine squared theta d theta. So then I can clean it up a little bit more before integrating. 4, 0 to pi, cosine squared theta d theta. So we need to integrate this bad boy, which requires a little Calc 2 knowledge there. So if you happen to remember the substitution for cosine squared, because you can't just simply use substitution or trig substitution or anything like that. You use a trig identity, well, substitution, but you're using a trig identity to replace the cosine squared theta. And that trig identity is 1 plus, I'll let you say it because it sounded like you had it.
1 plus sine squared.
Right idea. That if we're going to convert it over into sine form, it would be 1 minus sine squared. But then the caution there is if I replace a cosine squared with a sine squared, we really haven't improved the situation. What we want to do is we want to convert it over into a different type of function. Right? So this one involves a double angle identity, which is 1 plus cosine 2 theta over 2. Right? And it's one of those weird rules. I'll just kind of I'll just jot it down on the side here, or right below it. So the double angle rule for cosine, one of them, cosine 2 theta, is equal to 2 cosine squared theta minus 1. So all you did back in Calc 2, and the issue is with Calc 2, it's kind of like pre-calc in that you have a lot of disjointed topics that are sort of thrown together. And then if you have any hope of memorizing it, it's, it's a challenge, So all that happened here was we add a 1 to both sides. And we get cosine 2 theta plus 1 is equal to 2 cosine squared theta. And then divide out the 2. And so you end up with this formula, right? And that's how we handled, I'm kind of putting myself in spirit in your Calc 2 class. We handled trig functions, squared powers of sine and cosine that way. For even powers, we just replaced it with the appropriate trig identity, right? So we'd be looking at, well, we got the 4 on the interval of 0 to pi. We have 1 plus cosine 2 theta over 2 d theta. 2 goes into 4 twice. So a little bit of housekeeping just to make life a little bit easier. That's really all it comes down to. So 2, 0 to pi, 1 plus cosine 2 theta, d theta. Then we can integrate. All right, so we can integrate it separately because it's a sum, the 1 and the cosine 2 theta separate from one another. The antiderivative of 1 d theta would just be theta. The antiderivative, we talked about this last time, the antiderivative of cosine is sine. And we are assuming that it's going to have the same argument of 2 theta, but if I were to take the derivative of this, it would be sine 2 theta becoming cosine 2 theta, but then times the derivative of your inner function, which would be 2. So I'd have an extra 2 floating around if I just left my integral like this. I'm sorry, my antiderivative this way. So what I do is I correct for that by just chucking a 1/2 right in front. Right now it's up to you. You can do the u sub if you want. It's just I found in the past that people they prefer to do it this way because the u sub just adds more writing where it's not really necessary. So just again, a little recap on that. We know the antiderivative of cosine is sine, right? Not the derivative, the antiderivative. So then if I assume that the antiderivative of cosine of 2 theta is sine of 2 theta, then when I go to check it, sine becomes cosine, We keep the 2 theta, but then we have to multiply by the derivative of 2 theta, which would just be a 2. So that would have given me an extra 2 floating around there. So I chuck in the 1/2 in order to correct for that. All right. So then I can just pop in the pi. So we're almost there. So 2, we're looking at pi. Now, if I plug in a pi for theta here, I'm going to get the sine of 2 pi. Sine of 2 pi is equal to 0. So that second part is going to zero out. Right? So we don't have to write that. Then minus, plug in a 0, 0 for theta, and then plug in a 0 for theta again in the sine of 2 theta. Sine of 0 is also 0. So that thing zeroes out. We end up with just a 2 pi. Right? So now, this is a lot of work for something we already knew the answer going into, because we're looking at a circle with a radius of 2. So its area is going to be 4 pi by pi r squared. I only want the top half. 4 pi cut in half becomes 2 pi, but I needed to do the calculus. I needed to do the calculus in order to get credit for this problem. So there it is. That's the calculus. It would have been a whole lot more complicated, but if we had to do it for other parts, but I did the bare minimum there. Now, what I need to do is figure out what the area of that shaded region would be by subtracting from this value. So I have 2 pi. Subtract from it the 2 pi minus 4 that we came up with earlier. Okay. Distribute. The 2 pi's are going to go away, and we're just going to get, after all that, a shockingly simple 4. All right. And again, it doesn't have units, so it would be 4 square units. I'll make a note. So, or 4 units squared. But again, just be prepared to include the units on the test, any kind of assessment. Right, always important. All right, so definitely, that's a into the fire situation.